if you don't have questions for me, I have questions for you. Now, have seen this, like the concept of as you reduce your delta t, how fast does the error goes to 0? Doesn't just apply when you can do like mathematical analysis. It also is important when you empirically evaluate the error. That's particularly important when you are handed a computer code that you actually don't know what happens inside, all right, and you want to solve a problem where there is no analytical solution. How do you tell if the piece of code is complete junk or is actually giving you useful stuff?
Collect data.
Yeah, what data to collect?
Well, you go build whatever widget it is you're working on in a little scale, and you see if your code predicts what it does. And if the answer is no, you try a new code, and if the answer is yes, you build a bigger one.
Okay, so that's very good. So what's your name again?
Charlie.
What Charlie says is that go and do some field test and collect data. And if the data matches your computation, you are good. So that procedure is called validation, right? So you are validating whatever computation you're doing with real data. There is actually a step before validation. So the step before validation tries to save the disgrace of the computational simulation from being discarded simply because the person performing the simulation is not doing a well enough job. So whenever you do a simulation, you have to choose your delta t, right? You have to choose your discretization. And if you have chosen a poor discretization, it is not the problem of the simulator itself. So the step before validation is called verification. It's verifying that the equation, the numerical simulation is actually solving the mathematical equation you are trying to solve. While the validation is trying to see that the mathematical equations you are solving is actually any good, right? Are you missing key part of the physics that should be modeled, but you are not modeling? That's the job of validation. The job of verification is actually before that, is asking, is your numerics, is your approximation to your PDE good enough? That part is basically trying to figure out what is the order of accuracy. If the order of accuracy is 0, that means as you refine your simulation, you are not going anywhere. All right, that means like you have a piece of junk in your hand. If the order of accuracy is 1, it generally means you have a not very good piece of code. Because, okay, so if you're solving an ODE, first order is actually fine. But imagine if you have 3 spatial dimensions, which means you have dx, you have dy, you have dz, and you are integrating over time. You also have dt. First order accuracy means that if you refine every single dimension, delta x, delta y, delta z, delta t, by a factor of 10, your error is going to decrease by a factor of 10. Right? But to get that one more significant digit, how many times more computation are you spending? Generally
10 to the 4th.
10 to the 4th, right? You are spending 10,000 times as much computer time to get one more digit of accuracy. That's usually a bit too excessive. So in general, we are looking for at least a second order code, right? That's kind of the job of the person who is designing the algorithm of the simulation to get you at least a second order convergence. And now, how do you check that? How do you check that? Do a refinement. So, okay, so here's what I'm going to show you. How do you do refinement. Okay, so I have a code that computes me du dt. Here, I have a parameter that's called delta t, right? Okay, so what I'm going to do is I'm going to take this parameter out of the loop. Okay, so wait, my dt, I'm just going to first set it to 1. All right, and I'm going to for I refinement goes from 1 to, let's say, 5. I'm going to do 5 refinements. Actually, let me actually do a lot more. Do a 10 refinements. And I'm going to take this as a loop. For every refinement, I dt equal to dt times 0.5. I'm going to refine by a factor of 2. So when I compute the error, I don't compare against the analytical solution anymore. I compare with, if I refine is greater than 1, then I'm going to compare with my previous solution. Okay? So at the end of the loop, I'm going to say du dt 1 previous is equal to du dt 1. I'm going to copy that 3 times, and I'm going to record my previous du dt in a different array so that I don't overwrite it. And then I'm going to set my error 1 is going to be, I'm going to be using the same formula as when I compared against the analytical solution. I'm going to take actually the square root of the mean, just take the mean twice, of du dt 1, absolute value of du dt 1 minus du dt 1 previous square. All right, so that's my error. So I'm not comparing against the analytical solution. I'm just comparing one solution with the next one. Okay. And what do you think I'm gonna get? So here let me just say error 1 is equal to, because I'm gonna get one error for every refinement, right?
There's still du dt 1 to 3 previous.
Oh yeah, thanks. Yeah, thanks for debugging for me. I refine, let's say -1, so that I'm going to get a consistent array from 1 to 10. All right. So here, when I run this, did I get any? So if this is not greater than 1, then the problem is I don't have a du dt previous. I'm going to get an error because it is going to say this variable is not defined. Yeah.
Why is it I refined -1?
Because the first time I enter this loop is when I refine is equal to 2. All right. Okay. So, actually, I want to also have a dt array, right? So when I have this, I also want my dt array I refine is equal to dt. All right, so let me run this again. Okay, it runs. So I get, going to my workspace, I get an array of different dt's. Why does it start at 0.025? I thought I set it to 1. Oh, this has to be done here. Okay, right. Okay, so let me run this again. So the first one is 0.5, right? That's the first time I compare the error at 0.5 is when I compare my solution with delta t equal to 1 with delta t equal to 0.5. Okay, so then the critical part is I do a log plot. dt array and error 1. I don't have, let me close this one and let me put it like this. All right, what do I get? You see that clearly? Oh, you don't see the grid line. Screen is a little bit too bright for that. So yeah, you don't see the grid line, but you can see the grid spacing, right? So I get straight line in a log space. What does that mean?